you how to solve a PD into algebraic form. So already we know several discretization forms, central, forward, rearward, such a thing. So now, how to calculate the exact values of our particular PD? Because in the last lecture also we seen only in the derivative form. We still not apply the derivative form into a real time problem. So now this class is we need to apply that all the derivatives in the real time form. Okay, that is the objective. Okay, please cooperate with me. As well as when I ask any questions, I should ask question within this board. Okay, so give a quick response. Okay, so when you get a problem, with respect to your response, we will finish the solution. Okay. So consider one-dimensional heat transfer problem again. So X square. So apply FDCS scheme to displacement and whatever general analytical solution, it's a still high equation. To close this equation, I still need to be define boundary condition as well as initial condition. I have wrote here for this problem and this corresponding boundary condition and initial condition. Did you understand? So what's the meaning of this t of 0 comma d is 0 and t of 8 comma d is 0 as well as t of x comma d 1 by 2 x 8 minus x. Okay. And more in formal way, I can write this is x comma 0. So more form. So what's the meaning of these three values? This is our problem. Okay. And what's the form? This is x comma t form. I have write the boundary condition as x comma t. Okay. And the x is 0, time is as usual t, and x equal to 0, the temperature of my object is 0 of this node, and temperature distance 8 is also 0. So what's the length of this plate? It's around 8. Okay, 8 units. And each of the boundary also having a 0 degree temperature. Okay, this is the general physical meaning. So these two mathematical notation gives about the boundary condition of our problem. Is it? So this is boundary condition. And if you look at this condition, this is the initial condition. Why I am saying this is the form of x comma t. So temperature at t equal to 0 second, the temperature fluctuation in the rod, along the rod, the temperature distribution gives this solution. Means gives this function. Okay. So when you put the n number x value varying with respect to along the rod, you will get the temperature at particular location. So you have to say, so I can split up this as 1 node, 2, 3, 4, 5, 6, 7, and 8. This is 7. Because at the 8th location, this temperature is 0 from our boundary condition, 8 comma t, and the edge of the boundary is 0. Now, what I am interested in, I need to calculate all the temperature at each grid point. We have split up in the 8 grid points. So del x is time. Because of we will deal in the explicit form. So I will solve this problem in form of explicit. Okay. Apply explicit form. So this is the explicit approach I have used to solve this one-dimensional uncertainty question and corresponding initial boundary condition and initial condition. And as a user, I have fixed Lect. Okay, 1 unit. Because our 8 mode is enough. Even up to 3 o'clock it will take to find a fill up our solution. And that is your wish. Okay. For a stable solution, you can minimize your delta. Okay. So 1 by 8 is preferable. You can reduce to 1 by 4, 1 by 10, anything, so 1 by 8 is preferable. So if you want to check whether with respect to delta value is very in our problem, if you want to, you can change your delta for as a completion of classes, as a assignment. And I want to calculate x. This is the temperature. No idea. Okay. Okay. So such a net temperature is point. There still to be boundary point 8, 0 and 8 is a boundary point. So now initially I need to calculate due to 0 temperature. The question is arise. So there is no temperature difference between the rod. So how would we get the fluctuation in the rod? So that should be speaking in the initial condition. When you calculate the initial condition, you will understand where is the temperature is higher, minimum, where is the fluctuation area. Everything you can find out from the initial condition. That's why the scientist giving all the problem unsteady directly parabolic equation. Initial condition is first. That's why they are fixing initial condition. So initially what happened? What's the state of our system? What's the state of our rod? Okay. So now there is no temperature difference. How is temperature fluctuation? So this question can be answered by initial condition. Now pick your calculator, substitute T of 1, 0, what's the value, and T of 2, 0, T of 3, 0, T of 4, 0. T of 5, 0 up to T of 8, 0. So what's the value? T of 1, 0. When you substitute 1 here, you will get 3.5, good. And 2, 6, then 3, 7.4, 0. Calculate. 8 is it? 5, 0. 7.5. Then T of 6, 0. 7, 0. 8, 0. 6, 0. What's the value? 7, 0.
3.5.
Here?
0.
So these are the temperature fluctuation in the rod. Okay. Now I have to plot all the value to temperature which is x. Okay. So at the 1, 0, the temperature is, I can write as what's the maximum 8. So maximum I can put here 8. Okay. 1, 2, 8. Can adjust. some arbitrary value. Don't confuse with the load. It's not load, it's the temperature. You can consider it as centigrade. So 1 centigrade, 2 centigrade, up to 8 centigrade. That's how we are getting a maximum value is heat in the temperature scale. Okay. So at the first node, T comma 1 comma 0 is 3.5 and 2 comma 0 is 6. 3 comma 0 7.5 7.5 and 4 comma 0 is 8. That is the maximum value. This is 8. And if you look at the answer 8, it must be symmetry pattern. Okay, again 7.5, 6, 3.50, 5. So this is also another trick whether your boundary condition is satisfied or not. Definitely it comes to final state as a 0. Listen, don't find it now. Okay, finally it satisfies our initial condition. Because all it tends to 0, equal to 0. So and this is 0. 0 must be given. Temperature distribution of our pressure problem at T equal to 0. Okay. So time T equal to 0, the initial condition, we use the values of temperature distribution along the rod like this profile, parabolic profile. So now you can understand both ends are 0 temperature. Okay, both ends are with 0 temperature. And the mid of the plate, the mid of the rod having a maximum temperature. You understand? So maximum heat is supplied where?
Center of the plate.
Center of the rod. So the heat is supplied here. You can consider the heater is placing here. The heat is the maximum. It is propagate like in this direction. Okay. Maximum temperature definitely the near to heater, and gradually it has to reduce. Okay, that's the indication of this one. This section is the maximum temperature, and gradually it tends to 0. Okay, 0 value. So this is pattern gives from the initial condition. Now my question is, after the 0 second, when you can consider 1/8 second. It's around the 0.0125 second. Even not 1 second, highly sensitive, 0.0125 second, I can predict what's happening in temperature distribution along the rod. So this is the beauty of CFD. No one experiments not found here now in the world. You cannot find the temperature variation 0 second to 0.0125 second. It's impossible. But this kind of effect you can make by CFD. Now question is, I want to calculate temperature at T equal to greater than 0. Okay. So T equal to greater than 0, how would we get? I will apply FT series scheme here, discretize it by using explicit method. What's the value? How to discretize? T of I plus 1 minus I divided by del X del T alpha Ti plus 1 Ti minus 1 Ti over n divided by del X. So what's the objective? I want to calculate temperature update. after 0 seconds. I mean n plus 1 level. Nth level are now. Now I have to consider these are the nth level values. Did you understand? So these are the noun. At t equal to 0, I know value the nth level value. Nth level values already the yellow graph. Now how to calculate n plus 1 by using a FCS scheme? I can extract pi n plus 1 equal to alpha del t by del x square plus pi square. Is it? Now you can simplify. This is the constant value. Alpha I have made not given us. So you can consider alpha as 4. The property of material. Thermal diffusion. I have seen as a 4. So what happened? 4 into 1 by 8 divided by 1. Okay. Then Ti plus 1 at the nth level. Can change to yourself. Calculate this value alone. And this is x plus Ti plus 1. So what's the value? 0.5. So 0.5 times of so this is the general governing equation now. To solve our problem, so it's general governing equation. Now I want to calculate temperature at 1 to 8. Okay. Don't bother about the 8 points because of it's a known value by boundary condition. Okay. It's already given. The problem itself is given. 8, 0 is known. So we need to calculate temperature is I equal to 1. Substitute the 1 here. T1 n plus 1 equal to 0.5. T2 n and T0 n and T1 n. So I have to one. So substitute all the value. So this is now listen. This is I point. This is I plus 1. This is I minus 1. Okay. The 0 is temperature is 0. I plus 1. We have a temperature 6.6. Okay, 2, T2. So it is now T2. Again, for your reference, this is one the 0 point. 0, 1, 2, 3, 4. Okay, temperature 1, temperature 2, temperature 3, temperature 4, temperature 5. Okay, at the nth level we have plotted. Now substitute all the values into here. What happened? T2 is
6.
6. T0 0.
2
T1
2 into 3.5. 3.5
3.5
plus 3.5.
So it would be temperature 1 and 10 plus 1
3.
3. Okay. And similarly you can continue when I equal to 2. Substitute I equal to 2 in this equation, you will get T2 power n plus 1. Now substitute and tell me the answer. Likewise, T3 power
5
n plus 1, T4 power n plus 1, T power 5 n plus 1, T6 n plus 1. Now tell me
5.5.
5.5 degree centigrade, T3,
7.
7, T4, what about T4? What about T4?
7.5.
7.5. Then T5? Huh? 7.
5.5. 5.5.
5.5.
3.
3. T7? 0. T7 0. Check it whether 0 or not. T7.
Sir.
T7.
Sir. T7.
T7 only 3, yeah? Register. Okay. So T8. T8 n plus 1 is? T8.
0.
0. Now again, if you visualize such values, you can find out the pattern. It's also again the symmetry pattern with respect to maximum. Okay. So maximum value T4. At the location of T4, you look at the upper and lower values, definitely it's zeros. Again, sorry, symmetry. T1 power n plus 1 equal to 0, 0. Now 7, 7, 5.55. 3 is missing.
T1 power n plus 1 is equal to 3. 3.
This is that.
T1 power n plus
What I made a mistake.
Sir. Sir. Sir.
So T0 only is 0. Okay, T0. 5.5 and 3 and before T0 appears the T0 appears as 0. So again it forms after 0.0125 seconds. This delta is what's the value delta?
0.125.
What's the delta?
125.
125. Okay. So now plot all the values. So 0. Plot should be again at 1 T1 is
3.
3 and T2
5.5.
5.5. Okay. And T3
7.
around T4
7.5.
7.5. This must be symmetric. Okay. Because of heat is applied at the center of the rod. Okay, so propagate evenly, diffusion. Because of the right hand side of the equation, wherever presence of second order space derivative, that is another term is a diffusion term. So diffusion means it's a spreading, evenly spreading. That's why electric equation always is a diffusion equation. Diffusion terms are present in the electric equation. Both x and y are with respect to second order space difference. space derivative. Okay, dou square by dou x square, dou square by dou y square. Both are property variation takes place with respect to space and second order. So whenever sees this kind of setup in your equation, that is a diffusion equation. So another name of a Laplace equation is diffusion equation. Okay, it's a spreading constantly along a circumference. So this temperature distribution gives at t equal to 0.125 seconds. Okay. So this is for 0 second. So what happened? 0 second, yeah, 0 second, the temperature is maximum, and at 0.125 second it has to reduce. Its behavior is reduced, not increases. So what happens there?
Cooling.
The cooling process takes place, and heating the area here, and suddenly come back to our original temperature distribution. So definitely the heating propagates and it's suddenly decreases. So if you keep on your heater here, definitely this plot shifting towards beyond the yellow line. Okay. Now continue your problem. At t equal to 2 times of del t. Okay. Solve the same problem. T 1 n plus 2. We are calculating n plus 1. T 1 n plus 2. Solve yourself. And the procedure always same. Calculate these values. N plus 2.
T4.
So calculate. Solve Satya solve. ठीक है calculate कर
Sir, 2 times of del t.
And usually you can solve your problem with respect to now. All the temperatures being reference from here. Okay, don't take your initial condition now. With respect to initial condition, you have plotted yellow line. With respect to yellow line value, you have plotted pink line. With respect to pink line, you have to calculate. Now, next n plus 2. Understand? Now you have to consider your value as latest value. So these are the latest values. Now forget this value, initial condition values. This is the latest value. You have to substitute this latest value, calculating for n plus 2.
T1 2.75.
T1 is
2.75.
2.75.
75.
T2 5.05. 6.5. Well, here are. This is correct.
5, right?
5 or somebody told 5.25.
5.
This side, what's the value you are getting at T2 for n plus 2? because of so many students getting a 5 value. Maximum students answer will be considered. This is 7. This it must be 7.
2.75. 0.
0. T9 plus so can be the value at the one value, what's the value?
2.75.
2.75. 2.5. 2.95. Okay, that's that. Here. Temperature 2.
5.
5.
6.5.
So this is the value, temperature plot we have get T equal to 0. எவ்வளோடா 2 times of 0.125 0.5 or 0.25 0.25. Okay. Now if you keep on going, listen, the temperature plot should be diffuse the lowest set. Okay, all the temperatures tend to a bottom set. Finally, we will get steady state solution. So steady state means how the graph will propagate. Steady state means it must be line as. Finally, you will get this one after some time interval, and this may appear. Finally, the temperature distribution is mass. So it will appear like this. Okay. This kind of temperature pattern you will get when heating hits at the center point of rod. The temperature distribution takes place after time interval. 2 times of del T, 3 times of first time of del T. It means 2 times of del T, 3 times of del T, 4 times of del T, 5 times of del T, up to reaches a steady state. Okay. So this is a typical behavior. Now you can now feel your power of theory. As I said, in this minute values, you cannot take anything. Again, I am saying, because of that is a very important during analysis of our engineering problem. At the even second by second also you can calculate value. In the second itself, I have the dividend. Even you can fix your delta as a 1 by 100. Just we have taken for your simplicity 1 by 8. Okay. So if you want a more solution, micro scale also you can predict, but it's not realistic. For your understanding, I am saying. So that much of importance is present in a computational coherence. How many seconds you want to see? Okay. The flow pattern is variation with respect to time. Okay. Because of the parabolic problem, all the temperature, this fluctuation takes place. So fluctuation takes place with respect to time. It has to reduce. So that's why your graphics also unsteady. Okay. Right now. Problem, what happened when del T is increasing? So why we want to reduce the they substitute maximum value delta in the problem, what happens? Okay. So I can fix my delta as, you can choose delta as 5. Okay, substitute here, what we will be getting? Solve this problem again. We substitute 5 here, solve the answer. What will be
20.
It's around
20.
20. Is it? Again, solve the formulation for first iteration. What happens as T1? T1. Tell me the T1. Minus 60. 16.5. And here elsewhere minus 14. Here
T4 minus 12. T4 minus 12. T4
minus 12. Okay. And this minus 12 being on below the line. So when you put a heating element, there is no cooling effect. So this is also another concept in our common sense spelling. When heating element, definitely your medium not cool. It must be heat. Okay, so it must be gives any numeric value in the positive direction, but in the negative direction. So that's happening here. So when you increase your delta, you are breaking your constraint of an explicit scheme. So if you break into this explicit scheme in the delta, you will get a non-realistic value. Okay, so delta 5 gives non-physical sense. So that's why when I give a advantage, disadvantage in explicit form, the delta must be constant. Now you can understand. Okay. And another criteria also available. When you increase in delta, instability is also present. So always this instability leads to our problem divergence. Divergence means it's also again gives a non-realistic value, non-physical value. For example, when you take this kind of problem, in this plot, in 100 degrees, this is the 0 degree. How do you write down? Plot the temperature versus x. This is the 0 degree temperature, it's 100 along the line. How would you plot? The temperature profile must be straight line. Okay. Because the maximum temperature 100, minimum temperature 0. Okay. When you solve this kind of problem with the idea of a maximum delta, you will not get the temperature limit 100 to 0. So you will get definitely temperature in between the 0 to 100. Is it? This is the physical sense. We have 200, 250 degrees centigrade. Definitely you are going to wrong path. The problem is unstable. Leads to divergence. Okay. So this kind of phenomena occur when you increase in your delta, you will not get the realistic value. So how would you find out the realistic value? From our common sense. After getting a CFD value, you must check it out whether our value within the limit of maximum and minimum. Okay, maximum is 100, minimum is 0. So definitely our value is lying within this region. If it is great, definitely you are going to a wrong path. This problem is unstable. We have to reduce the delta. So again, the question is arising in your mind. What should be the delta value? How would you fixing the delta value? This will be in the next lecture. Okay. So there is constraint again. Delta must be some maximum value. Maximum I have to